Yo. Okay, shall we? Oh yeah, we should. Yeah.
The background, I leave it up to you all. It's your show. So, but for
I'm
me, I'll
just
do it
gonna-
because
I'm
I'm
just gonna do
advertising.
it.
Yeah.
I think we should put our SDS on.
I don't have that background though. Is it possible to send it?
I'll try to find it for you.
Okay.
I think I have it. I only saved the dark one. The dark background.
Okay. So you let me?
Yep. Okay.
Okay.
Yes, yeah.
Hello everyone. Welcome. It's an early morning, so let me just set stuff up. Open the view. So I should be sharing my screen right now. Do we just like admit all or like just let? I think we just open the take away the wait room lah. Okay, so I will be sharing my screen and I think we'll begin at about 10:05 because I see people are still streaming in. Okay, I think we can start now lah. I think most people seem to have come in. Okay, no, that's it. Just straight in. Let's wait another minute or so. Yeah, let's wait till the 10:05. Okay, so let's begin. Hello, everyone. Welcome. Good morning. It's a pretty early morning workshop. Hope you are ready. Maybe you all got like some coffee, and you're awake and ready to learn a little bit about machine learning. So we are from NUS-SDS and Data Science Society, doing this in collaboration with Orbital for this ML projects workshop series. So project series 1 and series 2. So let's, I guess, first introduce a little bit about ourselves. Here with us today is our current president, Harry. So Harry, please. Oops.
Yeah, thanks, Stefan, for the introduction. Yeah, so I'll give a brief introduction of what NUS-SDS is about. Next slide, please. Yeah, so who are we exactly? So NUS-SDS, we are officially under the Department of Stats and Data Science. So we are actually under the Faculty of Science, but we are open to students from all faculties. So for the last academic year, we have 75% of our students from science, while the other 25% are not from science. So as you can see in the pie chart, yeah, about 20% of them were from computing actually. And then we also had a student from architecture as well as another student from psychology. Yeah, so really we are committed to foster a community of students passionate about stats, data analytics, data science, machine learning, and more. Yeah, next slide, please. Yeah, so generally we have 4 main objectives for our CCA. So firstly is to enhance students' technical and industry relevant skills through the events and workshops that we organize. Then secondly is to support students in their academic and career planning endeavors. So this may be either through our routine career workshops or like through seniors imparting their knowledge to juniors. Yeah. And then for the third objective is for students to gain organizational experience and to contribute back to the student body. So of course, like when you join such a CCA, normally you get the chance to organize such events, such as this workshop. Yeah. And the last, but to me, most importantly, because at the end of the day, when you want to join a CCA, the main purpose is really to try and make friends. So you want to develop a hub for students to make real friendships and genuine connections in order to create a society focused on fostering a sense of belonging and togetherness. Yeah, next slide. So this is our structure right now. So we have the positions of president, secretary, treasurer, as well as our 2 vice presidents. And for the internal side of things, we have the publicity team. So they are in charge of our social media channels. And then the workshops team, they organize our technical workshops, just like this one right now. And then we also have a team XP or team experience. So they are our internal welfare unit. And they are in charge of organizing our internal society meetings to promote bonding between our fellow members. Yeah. And for the external side of things, again, we have 3 teams. So the first team is the events team. They will be in charge of organizing career-related talks or industry events, as well as merchandise sales, at least for the next academic year. And then we also have the Datathon team. So the Datathon team, they are the organizing committee for our annual data science or data analytics competition, which I will share a bit more later, as well as MSOC. So MSOC stands for Math and Stats Orientation Camp, where we organize our flagship orientation camp in conjunction with the Math Society. Yeah, next. Yeah, so these are our current leaders right now. Yeah, so I'm Harry. I'm year 2 going year 3 DSA or Data Science and Analytics. And we also have Ananya. She will be my Vice President Internal, as well as Rui Tong. She will be my Vice President External, from year 4 Statistics. Yeah, next slide, please. Yeah, so here are our society programs. So normally we organize 3 kinds of events. Firstly is the Datathon, then secondly is the technical workshops, and then lastly is the industry events. Yeah, next. Yeah, so firstly our Datathon or our annual data science or analytics competition. So this provides an exciting opportunity for hundreds of students to collaborate, compete, and learn new data science techniques. So what you see on the screen are our 2 most recent iterations of our annual competition. So the one on the left is our data analytics competition 2022 with Grab as our main dataset partner, while the one on the right is a poster of our competition in 2021. So the theme was more like computer vision with HP as our main dataset partner. For both competitions, I believe the sign-up rate was about 850 participants, which is very huge considering that especially for the last 2 years, they were mostly like online competitions. Yeah, next slide, please. Yeah, on top of the Datathon, we also have the technical workshops. So we conduct technical workshops ranging from topics like data science, machine learning, and stats tools, such as NumPy and Tidyverse, for learners of all levels. So whether you're a beginner or you're an expert who just wants to learn more, we have something for everyone. Yeah. So on the screen are just some examples of what the workshops team has organized over the past year, which was led by Stefan. Yeah. So we have data analysis fundamentals using NumPy and Pandas, as well as ML Ops architecture and system design, where Stefan actually reached out to the Singtel Digibank branch of Grab and then they organized an external workshop together. As well as data analysis in R, exploring the tidyverse. So if you guys are familiar with R, there are other different packages to explore, such as dplyr and ggplot2. Yeah, next slide, please. Yeah, we also have our career and industry events for students' professional development and endeavors. So again, we have 3 kinds of events. So firstly, it's a fireside chat with a data science professional. And then secondly is a career resume workshop that we organize in conjunction with NUS-CFG every year, as well as a data scientist alumni sharing session. So for this, right, we actually try to reach out to a recent NUS graduate to share more about his job and how his school experience led him to secure a job. Yeah, next slide, please. Yeah, so here are some other society initiatives that we've tried out, which are not purely academic. Yeah, so we have merchandise sales and then article submissions. So for article submissions, right, as long as there are students who are interested to write about like stats topics or data science topics, or even like module reviews, so we will invite these enthusiastic students to submit an article to us before we publish it for them using our website. Yeah. As well as a t-shirt design contest. So this t-shirt design contest is something new that was started just last year, where we invite everyone from NUS to design our new society shirt. And then this new society shirt will be sold usually in the 2nd semester. Yeah, the next slide, please. Yeah, again, we are not 100% work. We also have some fun time as well. So our internal society activities include stuff like team meals, badminton sessions, as well as our routine meetings and game sessions. So society level wise, we usually have our meetings once every 2 weeks, where the first part is more of like providing team updates to each other. And then the second part, because last year it was mostly online, so our game sessions were mostly held on Zoom. Yeah, but moving forward, we will try to hold more physical stuff, which I will talk about the movie night as well. So for the last academic year, we were fortunate enough that our very last society meeting was physical, where the respective members got to come down and interact with one another, as well as watch a short movie together. Yeah. And then lastly, we also have secret sharings. Yeah, so secret sharings, I believe this is like one of the key selling points of why people want to join our society, because we are fortunate enough to have senior members who want to share either more about their research or industry experience, and then the junior members will tend to benefit. Yeah, next slide, please. Yeah, so in case you guys are interested to join NUS-SDS, so this is the rough recruitment timeline. So right now, leaders recruitment or exco recruitment is still ongoing. Yeah, I'm still interviewing our potential next batch of leaders. So this will take until the next few days. Yeah. And then after that, once all the leaders are settled, right, we will open applications for potential members who want to join us to apply. Yeah, so this will happen around mid-July. And then afterwards, once we receive all the applications, we will interview the respective members, respectively. So this will likely take place until the start of August. Yeah, and just a short disclaimer, the above timeline is tentative. So this will depend on how the new batch of leaders want to plan the rough timeline out. Yeah. But if you are still interested to join us, do follow us on our various social media platforms for the latest updates. Yeah, next. Yeah, so this is our QR code. So this QR code will lead you to our various social platforms. Yeah, so maybe you can leave this on for like a minute or so in case anyone wants to scan the QR code. Yeah.
Okay. Thanks so much for sharing, Harry. I'll just leave it for like, about a minute for y'all to take a look. So 10:15, at least on my clock, we'll begin. Yeah.
Yeah, okay, I think 10:15 is up, at least on my clock. Yeah, so thanks once again, thanks Stefan for allowing me to share about the society. I'll now hand over the time back to you and your team to continue.
Okay, thanks so much. Don't hesitate to join. I'm a year 3 to coming year 4 computing science student. And I think 2 or 3 members of my team are also from SOC. So don't hesitate to join. It's a fun place. There are good things there to be had. Okay, so now let's get on with the workshop itself. So who are we? I'm Stefan. Previously already, I guess, introduced myself. Year 3 coming year 4, com science student. Currently interning in ByteDance, I guess. I guess just my socials. Barath.
Hello, I'm Bharat. I'm year 2 going year 3 data science major, and I've been a member of the Workshop Society for the last year. Excited to meet you all.
Yeah, and joining us is Rama, who will be helping us facilitate with the backend. Yeah. You just wave like you know what to say. Yeah, she waves. Okay. So then now we can begin lah. So let's just first go through what we are going to be talking about. So we're first going to introduce y'all to like the data processing pipeline all the way to training a model. And then talking about what's data pre-processing, how is it kind of done in industry, and then like in our own like little backyard projects, how we be doing it. Then Barath will be going through the introduction to machine learning, which is statistics, but better. Then introducing us to like neural networks, model tuning. Then after that, I'll come in at the end to see how we can get our own data from around the internet in a more automated and fast way, ethically as well. Yes. Okay, so if you have any questions about this slide, I think Rama, you can post the chat again in case people have not people have just come in or something. So if you have any questions, the Slido link is here. I think we do have like one or two interactive questions. There's a Slido tab thing. Oh yeah, you can see the numbering up there. Okay, so let's jump into the content. So introduction. So data processing pipeline all the way to training a model. So I guess we can first see, okay, is there a active poll? Is that, okay, never mind. I think that's a technical issue. So let's go to the introduction to machine learning / deep learning. So this field, right, the overall field that we are talking about is artificial intelligence. So if you're artificial intelligence, right, you might hear of this mod called 3243, CS3243. It's about intro to artificial intelligence. It's not actually like what you are more thinking about today, which is data-driven, where you're training some kind of model over data. That one includes like more algorithmic things like A* search or like some kind of heuristic-based search, which in reality is more like a graph search and more algorithmic rather than statistical. So where machine learning fits in is where we have a lot of data and we want to use prior knowledge about what we have today to predict what we have tomorrow in some sense. So machine learning now comes when we have a lot of compute power and a lot of data, and we want to make use of that data to build value. And deep learning is a subset of machine learning, which is a specialization using this concept called neural networks, which Barath will be going through later. So it's a subset of machine learning, which is also a subset of AI research in general. So when we want to talk about like models, we need to see what's the pipeline behind it. So in the industry, what they would do is they will have internal products that they collect data from. They'll store it into data warehouses, data marts, data lakes. These are few buzzwords that they use. Then after that, they enrich it, they clean it, or they transform it in some way. Then after that, they use it, apply it into a model that they then train and then use to visualize, or in our case, they'll be used to predict and spit out a prediction. So in the context of software engineering, it would be most likely that what you would be using machine learning for is not in this pipeline itself. So this is like how we get a model that we want to use. In the context of software engineering, what we would usually be using it for, it'll be serving as either a core functionality, it'll be a feature itself, or a backend component. So what does that mean? Sentiment, for example, in this sentiment analysis, there's this greed and fear index for crypto markets based on Bitcoin. that you can actually go and Google about it right now. Basically, it tracks like how fearful or how optimistic people are about crypto in general, and it has shown to be quite a useful signal for prices lah. Although right now, as you can see, it's extreme fear, and my own wallet is also tanking. The second is the zoom background. For example, this zoom background behind me here, you can't see my messy cupboard over there. And yeah, it serves as a feature of the core offering of Zoom and enhances its like view. The third way it can serve is like as a back-end component. For example, in TikTok, we use machine learning models like XGBoost or whatever to recommend people different videos. So like that serves as a back-end recommendation system that is used to drive, I guess, content recommendation for the users, which then drives ad revenue, which then drives the business of TikTok. So these are the more expected areas that you might use machine learning for in the industry. Although I'm not sure what all of you are doing, it could be something more creative than these. Okay, next, now that we've gotten an overview, I'll talk about data pre-processing. So what is it and how is data pre-processing done? So this is going to be at a higher level. So it won't be so generic. It'll be a little bit more generalized. So it won't be so generic to like what specific topic you're on. And we will be providing links to the slides later on so that you can do some further reading on your own. And it is in fact encouraged that you will do so behind this because it's quite a big field and each type has its own kind of models. So data pre-processing. Data pre-processing comes in four main ways. There's data cleaning, where we delete incomplete, incorrect, or irrelevant data. For example, if you have tabular data, you have a lot of null values, one row is like very bad or whatever, you will want to drop that row and you want to replace it. And if you want to keep that row, because perhaps it's an important feature, quote unquote, you'll want to maybe impute a value into that data in order to repair it and make it serviceable for putting into a model. The second thing is also instance selection. We need to be able to identify like how many classes that we want to search. This would involve a lot of exploratory data analysis. Normalization, this is a way to make our data more so appear normally distributed, which makes it more useful for data analysis in conventional means. And then transformation. We transform data into different ways and means as required. For example, if you're working with image data, maybe you're using a different format and you want to convert it to RGB values. So these are some of the ways that you can transform. So sources of data. Luckily, we are living in the world of the internet with a lot of big data everywhere. So there are many, many sources. You can go to Kaggle. You can find a lot of base data. You can go to UCI machine learning repo. Google has their own image data set search. There's AWS, there's Azure, there's even like data.gov. In the links below, in the slides links below, we will show you, we will like have links that go to these different places where you can find more data. So we also need to, so let's go a little bit into it. So today we'll be working with some image data. So we need to inspect our data. So exploratory data analysis, EDA, is important to check our data is going well, is correct, it's not like mislabeled as a sanity check. This is not just limited to image data that we're working with, but also textual data and whatnot. Particularly would be like if you have already labeled data, perhaps it was automatically labeled by some kind of algorithm. We want to ensure that it's of high quality. Like for this one on the right here, it looks reminiscent of a cat once you look at it a lot, but you'll need to inspect it to ensure that it really looks like that lah. And also you want to check for class imbalances in the data through exploring like the class labeling lah, in using some Python script lah. Yeah. So cleaning and pre-processing your data is usually very domain specific. So I recommend you check out these workshops or videos for more info on like common types of data. For example, like computer vision, there's a whole module on it, and it wouldn't be so easy to go through all of it at once. So this is stuff that is recommended for you based on what use case you're looking for lah. Okay, now I pass the time to Barath to introduce us to a bit on machine learning and take us through the next steps in our little journey. Yeah.
Thank you, Stefan. All right, just give me a second. Need to set up one thing. Second. By the way, at any time in my presentation, feel free to ask in the Zoom chat or in the Slido, or like if it's really urgent or something like that. If you have like a really pressing doubt, you can also unmute whenever there's like a beep in the presentation. So unmute and ask. So anyway, let's get started with a brief intro to machine learning. So machine learning is basically a fancier version of statistical inference. So let's look at what exactly machine learning is. All right. So what is machine learning? So let's ask Google about that, shall we? So when we basically Google up the definition of machine learning, it basically says that machine learning is the use and development of computer systems that are able to learn and adapt without following explicit instructions by using algorithms and statistical models to analyze and draw inferences from patterns in the data. So this definition definitely seems a little bit on the wordy side. So let's see if let's see if there's a way that we can improve upon it or make it more simple. So let's examine two flows. Let's look at a non-machine learning approach, and let's look at a machine learning approach for the same data. So in the non-machine learning approach, we'll basically have our raw data, and it's up to us to basically infer rules and basically like make decisions as to what the computer should do. And then we have to encode these rules and decisions into the computer. Now, what we do in the machine learning approach is that we have the data set, and then we decide based on the data set, what sort of algorithm should the computer use to automatically infer rules and such from the data. Now you might be wondering, why is this necessary? Why do we want machine learning in the first place? In what time is this useful? Seems like a bunch of extra work, right? Well then, machine learning is good for problems where it's just too complex to actually manually infer rules. And then some other use cases of machine learning are when you basically have a changing set of data with the underlying rules in flux. So for example, when you have recommender systems for apps like TikTok or YouTube, trends basically rise and die in a matter of weeks if they're lucky. Sometimes they just die out in a day or so. So that is why, in order to quickly adjust the algorithms under the hood and to basically like keep recommendations more up to date, they utilize machine learning. And speaking of TikTok and YouTube, machine learning is also used for addressing problems on a scale. For example, in the case of YouTube, if I remember correctly, there's more than 1 billion hours of video on the platform. So reviewing that much content would basically take a human about 1 billion hours, which isn't feasible at all. So in that case, you have machine learning algorithms that have been trained to basically detect copyright infringement and stuff like that. So it's basically able to address problems on a scale that humans cannot even dream of. And that is why we end up using machine learning in many facets of our day-to-day life. Now, as for how machine learning works, as in like the types of machine learning, well, then here's a quick and simple flow chart to basically get you started on the general direction in which you should be doing your machine learning. So first is, do you have the true values of what you want to measure? If not, then it's an unsupervised machine learning problem, which has its own set of algorithms and stuff like that, which we won't be able to get into right now. If you do have the labels or the true values, then it is a supervised learning problem. And then you have to ask yourself, do I want to classify something into categories, or do I want to estimate a continuous value? If you want to classify stuff into various categories, then it is a classification problem. And if you want to estimate their various values, then it's a regression problem. Now, we'll be talking about neural networks, which are mainly in the category of supervised learning. Whereas for unsupervised learning, you have stuff like clustering, principal component analysis, and anomaly detection. However, there are other types of machine learning out there, such as semi-supervised learning, which neural networks with something known as an autoencoder are big fans of. And you also have reinforcement learning, which can be done with neural nets or with like more conventional algorithms. In short, do a lot of research before deciding what approach you want to use. Now, here are some non-neural net models that you might want to consider. By the way, all of these are very accessible in Python with the scikit-learn framework. So that is something that you may want to keep in mind. So here you basically have a simple linear regression, which is used for no points for guessing, regression. Then you have logistic regression, which is used again for classification this time. Then after that, you have the support vector machine, which is mainly used for classification, although I know that sklearn has a support vector regressor in there. So that is one thing that you may want to keep in mind. Then we basically have stuff like random forests and decision trees, which are surprisingly useful. And we have the 9-base classifier, which is pretty good for when you have more probabilistic scenarios. Now, we have all of these algorithms, but then the main question is, how do we make a machine learn? Well, then the answer is simple. We train the machine. And then we'll have to ask ourselves, well, then how do we know that the machine learning model is working? Well, then that much is also obvious. We need to test it. So how do we go about that? We basically split our data. We basically split our data into two parts. We split it up into a test set and a non-test set. And now our test set is something that we basically split off very, very early and that we do not touch until our model is ready. Can anyone tell me why we don't want to basically touch our test data at all until our model is completely ready? You can basically indicate in the Zoom chat, or you can shout out the answer if you want. Exactly. It's to prevent bias, because what happens is that if you basically keep running your models on test data, you basically end up getting an overly optimistic estimate of the model's performance. So you effectively fit your model's parameters to the test data itself. So the test data is supposed to give you an accurate visualization of how your model actually performs in the field. So one thing that you should not be doing is basically repeatedly running code on your test data. Now what we do is that we basically then split our non-test set into a training set and a validation set. So our training set is what we train our model on, and our validation set is what we use to adjust our model performance, to change our model performance while adjusting it. So there are certain parameters, if you look into later, known as hyperparameters, that affect how your model is trained. So we'll basically test our model performance on this validation set in that case. Now we basically now we can get into the meat of this presentation, which is the introduction to deep learning, going deeper with neural networks. So the thing is that some problems are hard. Image classification is a hard problem to solve classically. Natural language processing is also rather hard to make something that sounds like a human being and not like a text-to-speech, not like Cleverbot in the 90s. So what we need to do is that we need to figure out how to mimic, we need to figure out how to solve those problems. And we know one structure that is able to solve those problems very well. And that's up here, our human brain. So what we do is that we basically take inspiration from the human brain. And what's the basic unit of the human brain? The neuron. So what does the neuron do? Well, then, to overly simplify it, and I know that the biology majors are going to be cringing at me right now, but a neuron basically takes in various signals as inputs, and it gives out a signal as an output. Simple, right? So what we need to do is that we need to try and then mimic this basic unit of information as in a way that a computer can understand. So effectively, this is our artificial neuron. So an artificial neuron basically has various inputs over here, and you have your output node right here. So this output node basically gives you a value known as the activation of the neuron. Basically, activation value closer to 1 means that the neuron is going to be very, very active, and a value of close to 0 means that it's not at all active. It doesn't care. Now, the thing is that like not all inputs are created equal for every neuron, and we need to make sure that different inputs have different weights. So therefore, we basically add weights to each one of the connections between our input and our output neuron. And then what we do is that we basically end up getting an output from the neuron. How do we calculate this output? Well, then the most basic way to calculate an output is by simply using a weighted sum. So what we do is that we basically just use a weighted sum of the inputs plus the output weight, plus the weights times the weights to basically get our output. Now you might see this bias term over here. This bias term is basically to ensure that we have this constant component in our function. Can anyone tell me in the chat, in 3D space, what does this function actually represent? Like in the chat or in the Slido or unmute, what would this function actually represent in 3D space? It is a dot product, sure, but then I'm talking about a geometric interpretation. All right, simpler question. What does mx plus c, y is equal to mx plus c, represent in 2D space? It represents a straight line, right? So then an analogy would be in 3D space, this sort of equation would basically represent a plane, correct? So now you might be wondering, why am I getting into this sort of interpretation? And that is to tell you the problems of having only one neuron. Because the neuron can only represent that one function of a dot product of an x term and a set of weights, it can only represent one plane, one hyperplane in space. So what happens is that if you wanted to separate stuff in 2 dimensions, for example, you're only allowed to use one line to separate them, using only one neuron, or a perceptron as it's called. So is there any way for us to actually separate these 2 sets of points by only using one line? No, right? You can try this. Doesn't work. Doesn't work. This guy is misclassified. Doesn't work. These 2 guys end up being completely misclassified. So you can actually see, right? You basically can't. There are some problems that we can't exactly solve with only one neuron. And it's not just some. This is a very basic problem. This is the XOR problem. So if we can't even solve the XOR problem with one neuron, well, then what do? Well, then we just need to stack the neurons. We just need to add a ton of neurons together. But then even adding a ton of neurons together, we have a problem. We can't separate an XOR. But then how do we deal with a situation like this? We know anyone, by just looking at it, we can see that we have a circle, that the correct answer is a circle. And people might be saying you can use stuff like transforming variables and stuff like that. But then how do we ensure that this works for a general case? Well, then the answer is actually rather simple. We know that we are restricted to linear functions in our neural net. And that is mainly because the perceptron basically only has linear functions in it. So what we need to do is that we need to introduce some nonlinearity. And we introduce this nonlinearity using something known as an activation function. So it is actually provable that a neural network with an activation function can actually approximate any sort of, any function. And you can actually look up universal approximation theorem to actually read up more about that. It's a very interesting read. So now we move on to more common activation functions. So some common activation functions are ReLU. You'll see this a lot. It's basically one of the most favorite ones of people today. And ReLU is basically saying, ReLU basically tells us if it's below 0, the value is 0. If it's above 0, the value is as is. Next, we have Sigmoid, which basically squishes the entire domain from -infinity to infinity between 0 to 1. So values, obviously 0 would be 0.5, which means that we can't exactly make a decision. And then tanh basically does the same thing as sigmoid, but then it squishes everything from -1 to 1. tanh has its uses in more advanced networks. I think there is a tanh gate in an LSTM cell, which is a more advanced type of neural network. Now, let's run with it, shall we? So we have our perceptron, we have our activation function. We know that by UAT, we can approximate any function. So we haven't forgotten anything, right? Unfortunately, there is something that we have forgotten. We have forgotten how our model actually gets trained. Understanding the training process is something that is extremely important for understanding how a model works. So how do we train a neural network? For that, we need to ask, how does a neural network learn? And since neural networks are based on the human brain, we can ask ourselves, how does a person learn? Well, then a person learns by trying out problems, right? Then we see how badly we messed up on those problems. Then we'll basically see how to improve. We'll basically look at what aspects of our thought process were to blame. Then we'll make the necessary changes, and then we'll repeat the entire cycle again. Neural networks learn in almost the same way. They basically go through the process of feed forward to basically check their current performance. Then they go into a stage of loss calculation to see how badly they messed up. Then they go into the process of back propagation to see where to improve and what exact parameters need to be changed and by how much. And then they make the necessary changes by using gradient descent. Now, feed forward is the key idea of feed forward is to feed some data into the network and receive the output of the network. So you have your little network over here, you have your data goes in, and you get the output. So effectively, information flows from data to the output through the neural network. Simple enough to understand, right? By the way, feel free to interrupt, feel free to ping on chat or on Slido if you have any questions, because it may get a little bit complicated now. Now, loss calculation, the key idea is to calculate how off our prediction is. How badly did our model perform? So now, based on the type of machine learning model that we do, we use different functions known as loss functions or cost functions to figure out how badly our model is doing. So you effectively have two types of loss functions for regression, which are mean squared error and mean absolute error. There are many more. Like the number of loss functions is basically infinite and will depend on problem to problem. Then for classification problems, you have hinge loss, although cross entropy is the most widely used one as of now. Then you basically have, just get the loss out of considering whether or not it's a regression classification problem, and you calculate the loss of the expected predictions versus the actual values of the predictions. Then what we do is that we need to so it's not very helpful to only know that we've done something wrong or how badly we've done something wrong. What we need to do is that we need to figure out what exact parameters, what exact components of the network are to blame. So effectively, we need to assign a certain amount of blame to every parameter, saying that this parameter is responsible to this extent for our model being wrong. So how do we do that? Well, then we know that the loss should go down, right? The loss is dependent on the output. So how do we change the output to change the loss? And then but then we have to look at what the output is dependent on. The output is dependent on layer n, the last layer of our network. And it's dependent on the activations of layer n and the weights and biases that lead from layer n to the output. So what we can do is that we know that the activation of layer n is dependent on layer n minus 1. And we know that we can actually change the weights and biases now because those aren't dependent on any previous parameters of the model. So what we do is that we basically see, okay, fine. Is it something that's dependent on a previous parameter? If so, then I'm going to go to that previous parameter to assign blame for that. But then is it dependent on something in and of itself? Is it not dependent on any previous parameter? Then change it. So you basically do a similar thing with layer n minus 1. It has its own activations, its own weights, its own biases. And then you basically change that out. And you go to layer n minus 2. And so effectively, information will flow from the output all the way up to the input data. You don't change the input data, obviously, but then everything until the input layer ends up getting changed. So what ends up happening is that information propagates backwards, right? Hence back propagation. So if you want a more mathematical understanding, I've actually shared some resources in before the workshop itself. That is an excellent resource for getting a more mathematical grounding on the calculus that underlies this main idea of assigning blame to each parameter. Now, the thing is that like it's not enough to simply just assign blame to the parameters, right? It's not so good if someone just lays blame on you. What you need is constructive criticism, right? And that's what the parameters of our machine learning model need. They need to be given a direction to improve in, right? So what we need to do is that from that blame score that we get from our backpropagation algorithm, we need to make the suggested changes to the parameters of our model, and we need to nudge them in the direction of the change. We need to basically like make small changes at a time. So how big of a nudge do we want to make it? Well, then the thing is that like it's very easy to determine it. What if the parameter has a very large, causes a very large deviation in the output? What do we want to do then? Does anyone want to enter in the chat? Well, then, if the parameter causes a very large deviation in the output, then yes, exactly, we'll want to nudge it harder. We'll want to give it a big nudge. And if it causes only a small deviation in the expected output, then we'll want to give it a very small nudge, right? So this is what gradient descent actually handles for us. So now that we're actually, here's a quick animation of how gradient descent actually works. Notice that it basically, this is something known as the loss surface. It's basically like you have two parameters, and then you have the costs basically going down, and then you have the cost being represented on the z-axis. So notice how the loss actually represented by this point actually keeps going downwards in the z direction as you get a better and better fit as you go through more and more epochs. So this is actually the process of gradient descent that actually this is actually the same process of gradient descent that actually happens in neural nets. So let's take a break for some questions, because I know that it's been a little bit, it's been rather, this may be a lot to take in. So we'll come back at around 6:52. So if you have any questions, you can ask on the Slido, or you can basically like unmute and ask, or you can ask me on chat.
Yep. So I think we'll take a 4 to how many minutes was it, Bara?
6:52. So
yeah, so about a 5-minute break. Feel free to ask questions, yo. Okay, I think there's some questions here. I will address the difference between scikit-learn, TensorFlow, and PyTorch libraries. Okay, so there is a big difference between scikit-learn and the other two. So what's scikit-learn? Scikit-learn is essentially a Python library containing a lot of machine learning algorithms that are implemented with a simple and easy to use what you call it, kind of library design, where like each model is like it's an object in the library. So it's a pretty big library with a wide range of different machine learning domain. Actually, it's my camera on. Okay, yeah, a lot of different machine learning domain models, like That's so not including like, not just including deep learn, or rather it's not including deep learning models. So that's the main distinguishing point between scikit-learn and the other two. So TensorFlow and PyTorch, they are more similar in that they are both catered towards deep learning. So meaning they make use of your GPU. Yeah, the thing that is pretty expensive now that people are using to mine crypto. Scikit-learn is more so catered towards machine learning, like k nearest neighbors for unsupervised or decision trees, stuff like that. TensorFlow and PyTorch are catering towards deep learning. So that's where you have what you'll be learning later on, which will be a bit of TensorFlow on model layers down to even like the individual like tensor kind of area. So the difference between TensorFlow and PyTorch, there isn't a huge difference, but I think PyTorch is more Pythonic. Then TensorFlow is more, it's a bit more production ready in some sense. Like there's a more mature support for TensorFlow in terms of like how you can deploy it. While PyTorch is used a bit more in like research, if I'm not wrong.
Yeah, PyTorch is mainly a research-focused project. So if you actually look at research papers, they'll usually give code either in C++ or in PyTorch.
Yeah. The other thing, could you share the resources on the map behind backpropagation? I think it's been shared in the chat. If you want to find those somewhere else, is I think in the description for like the pre-reading for mission control tree, that document.
All right. I think we should be getting back to it. So I'll give everyone like a minute to basically get back to the to basically like access the collab and everything. All right. So I'm going to assume that everyone's made it over onto the collab file. So now here is a little bit of so first Google Colab is like an excellent way to deal with to basically do machine learning and stuff like that. Although the time limits might be a little bit annoying whenever you have long training sessions. So just keep that in mind. The advantage of it is that it doesn't actually run on your own computer. So people like me with M1 Max, which famously do have a lot of problems handling TensorFlow, are rather safe when using TensorFlow over here. Now we basically just have like the first few cells are just like some import handling and setting up TensorBoard. TensorBoard is an excellent way to basically track your model's performance and to basically like help optimize hyperparameters more easily, which we'll see a little bit later. Now, you basically have the data pre-processing. So what we do is that we basically load in this data from the CFAR10 dataset. So the CFAR10 dataset is a pretty standard image classification dataset. It contains around how many? 60,000 32 by 32 images, split 5:1 between non-test and test sets. So then what we need to do is that for the purposes of our demonstration today, we're going to ask the question, can a computer tell apart a cat from a dog? So in that case, we need to basically filter out our data to only include cat and dog images. And this is done with like a very rudimentary thing of like slicing and subsetting and stuff like that. This is mainly just NumPy. This is just mainly like NumPy and you should be able to find out how to do this basically anywhere. So examining the data, which is one of the first steps for our model, we can actually see that, okay, fine. It's basically all clean because this is a ready-made data set for us. So we don't have to do much pre-processing. However, when we're examining the data, it basically gives you the RGB values for every single pixel, which is not great if you are if you have a human sense of vision. So instead, what you can do is that you can import matplotlib pyplot, and you can basically do plt.imshow with this array to basically get a rudimentary picture. Does anyone want to guess what this picture is of? Yeah, yes, just a cat. So you can actually see over here for the purposes of basically relabeled our model to basically give you a value of 1 if it's a cat, and a value of 0 because if it's a dog. So now moving on to the model building portion. The thing is that, like, I've defined this function known as get results to basically just quickly give a quick confusion matrix as well as the accuracy score for every model. So we can quickly see at a glance how the models are doing. Now we basically define our network. So here I'm using the TensorFlow functional API to define the model, which is much more flexible. And it is what I would honestly suggest that people use rather than the sequential one, which seems easier syntactically, but then it makes your models a lot more rigid. So effectively, you have an input layer, then you basically have a set of computations that you need to do, because a neural network at the end of the day is just a set of computations with different layers, correct? So effectively, you're taking our input, we're flattening it out, then we're feeding it into 2 dense layers to finally get the output at the end. So then what we need to do is that we need to set some learning parameters. So these are the hyperparameters that I was talking about, and we'll get to them shortly. So then what we do is that we'll basically compile our model using a model name.compile. We'll need to specify the optimizer and the loss, and then we'll need to specify the metrics that we want to track in every iteration. So you can track accuracy, you can track precision, you can track recall, and so on. Then what we do is that we basically need to begin with training our model. So what we also do is that we basically add a callback to TensorBoard so that we can actually look at how the model performs in TensorBoard. So we basically train this guy for 20 epochs, and we can actually see that, yeah, the results aren't too great. It's 55%, which is barely better than flipping a coin. So what went wrong over here? Why is our machine learning model performing so poorly? Well, then for that, we'll need to actually dive into the wonderful world of model tuning, which is the next segment in our presentation. Just give me a second over here. Yeah, all right. So model tuning is basically the process of adjusting various model parameters to ensure that we get the best performance out of our network. So the parameters that we tune during the model tuning phase are the hyperparameters. So these are parameters that are decided before we train a model. So these have a huge influence on the training process and what outcome we actually get. So so examples of model parameters that we look into are the model architecture, the learning rate, and the number of epochs that we train a model on. So what exactly is model architecture? Well, then model architecture is basically the parameters along with the overall structure of the model. So stuff like how deep our model is, or how many layers that we have in the model, or how big, how wide are the layers, how many neurons do we have per layer. All of these are actually determined by the model architecture. So in the same way that you would design a hotel and a home very, very differently from each other, model architecture, the different models with different architectures are useful for different purposes. So for example, if you wanted to do an image identification task, you wouldn't actually use a normal feed-forward neural network. You would use something known as a convolutional neural network to actually to do image identification. And if I remember correctly, for natural language processing, the current state of the art are recurrent neural networks as well as transformer models. So in that case, let's actually go back to our collab. So looking back into our collab, we can basically see that our first iteration is subpar. So then what we need to do is that we need to basically, so let's try a deeper neural network. Surely more parameters means better, right? Deeper means better, surely. So what we do is that we've added another layer, and then we've just like run it again for another 20 cycles. And you can actually see that the accuracy sort of dropped. So the thing is that like deeper network does not always mean a better network. What you need to do is that you need to actually look at the type of architecture that is actually best for the given problem. And as I mentioned earlier, this is an image classification task, is it not? So therefore, the better model to use is a CNN model, a convolutional neural network. So therefore, we basically start off with a basic CNN network. So you basically start off with a convolutional 2D layer. Then you have a global average pooling. So you have a convolutional layer to get various filters, and then you pool the highest value. Then what you do is that you then pass it into 3 dense layers. So then what we do is that we have the other, everything else stays the same. And then we basically train our model for a while. So you can see that we actually get a decent improvement on our accuracy. We're now pushing 58.7%, which is good considering that we started off with basically coin flipping. So looking at the tensor board, yeah, you can actually see that it seems pretty good. But then we actually see one issue, right? TensorBoard automatically smooths the loss, but you can actually see that the loss is actually rather chaotic in nature. So how do we fix this? Well, then that brings us to the second hyperparameter that we will want to tune today. And that will be the learning rate. The learning rate is basically a multiplier on the nudge segregated descent gives. So what ends up happening is that it becomes a Goldilocks-like situation for us. Because if the learning rate is too small, then that means that the model will take forever to converge to the correct set of parameters. But then if the learning rate is too high, it can basically end up bouncing out of a local minimum, and the model can basically just diverge, which basically means that you won't get to a set of fixed values. You can actually see that our deeper ANN actually suffered from the latter problem right over there, if you actually look at the TensorBoard callbacks. Then, so what do we do instead? So we need to basically try and optimize our learning rate to be just right. So what we can do is that, moving back to our collab, we can see that, all right, with a lower training, we've actually lowered the learning rate over here to a tenth of what it was. I think right now it's 10 to the power of -4. It was 10 to the power of -3 before. And unfortunately, you can actually see that something basically ended up going wrong with our model right over here. So stuff like this does tend to happen at times. And I think that the solution for this is but then the thing is that like such stuff does tend to happen with deep learning models at times. And then you just need to keep experimenting further. So the thing is that like there might be some issue with overfitting in this case, where our model has basically adapted highly to the test set, to our training set, and is not performing well on validation. So what we need to do is that we need to basically try to knock out random neurons in each training example. So what knocking out certain neurons in every training example does is it actually removes dependence on any one particular neuron, making it more robust in its predictions. So moving on to our basic CNN network with a lower learning rate plus dropout, we can actually see that going through over here with a single dropout layer being added, we can actually see that the accuracy is actually jumped up to, and we're now actually hitting 60%, which is pretty good, all things considered. we can actually see that we actually probably can get away with training our model for a bit longer, which is something that, yeah, it needs to be optimized, and then you just need to keep working on trying to optimize it further. So now let's talk about this. Now you remember I talked about overfitting versus underfitting. Well, then that is actually a huge problem with machine learning. So let's look at it. So the thing is that sometimes our models might not be performing as well as they want it, as well as we want it to, right? So if our model suffers from poor performance, there may be two things that are to blame. So there are two things that we might need to look out for, and that is underfitting or overfitting a model. Now, neither of these are particularly good news for us. So let's look at it. So the key idea that underlies both underfitting and overfitting is an idea from basic statistics, which is the fact that the total error is basically the sum of the error from bias plus the error from variance. So to get an explanation of what bias versus variance error is, you basically have a look at this picture right over here. So you can see that bias basically means a high bias just means that your predictions are all consistently off from the target. Whereas a high variance basically just means that your predictions are more scattered. So that basically means that so what ends up happening is that in machine learning, the more complex our model is, the lower our bias error is, and the higher our variance error is. So the thing is that there is no such thing as a completely errorless model. There will always be some trade-off between bias error versus variance error. So the key is to find out the right balance of parameters that actually get you to the best possible state. So what exactly is underfitting? Well, then underfitting is when the model is unable to capture the true trend of the data. You basically use too rigid of a hypothesis. So for example, these sets of points over here can obviously be separated by a curve, right? But then if you only allow the separator to be a line, your model performance is going to suffer. So what ends up happening in the case of underfitting is that you have a high training error along with a high test error. So does anyone want to actually suggest any solutions to solve the underfit? You can actually go to Slido and then you can actually type out your responses. It's completely anonymous. So just give out your wildest ideas on how to fix underfit, having heard of what it is. Introduce more non-linearity. Yes. Make the model more complex. Increase complexity. The hyperparameters influence the complexity of the model. So that is one thing that you need to, Yep, exactly. So the idea for solving underfit is to increase complexity. You train the model for longer. You let the model adapt to the data more, or you basically make the model effectively more smart. You basically reduce the dropout layers that you have in the model and stuff like that. Next, overfitting is a much more pernicious problem. The model ends up capturing the trend as well as the noise. So effectively, overfitting is that one kid who basically goes to school, who basically goes to the exam, only having ever memorized every single problem in the textbook and is stumped whenever there is a problem that comes from outside of the syllabus. So the idea is that an overfit model has basically just memorized all of the spurious associations in the data. And effectively, the prediction part of that model is pretty useless because it's just become a lookup table effectively. So that is overfitting. And can anyone tell me how do we want to fix overfitting? Increase regularization parameter. Yes. Okay. So regularization is a way to fix overfitting. Regularization basically gives you a cap on how complex your parameters can be. So that is one way to definitely fix it. Train less. Yes. You train for fewer epochs. Yes. To give it less time to give it less time to memorize the data. Then you also reduce the complexity of your model. Yes. You basically either take fewer layers or you basically reduce the size of each layer and stuff like that, or you add don't train on test. The thing is that like we aren't supposed to train on test set. That is a general rule for everything in general. That's a rule for all machine learning in general. Convolution is the thing is that convolution is just a different model architecture. So it is one way of making our model more adaptable to the training data, but you can still overfit on an image training problem with a convolutional layer. So that isn't exactly the way that we should be going about it. So here's like a brief summary. You guys have already given most of the points already, so I'll be quick about it. So underfitting is a much more rare case, and the solution for these are very simple. You have to train a model for more epochs, and you have to make the model much more complex. And overfitting is much more common than underfitting. You'll actually see this a lot more. And the thing is that the solutions are training for fewer epochs, make the model less complex, deliberately hamper the network. So dropout, and as one of our friends mentioned over here, regularization are very useful ways on actually preventing overfit on our model. Then let us basically go into like a more finely tuned model. So over here, you basically see that we are able to hit an accuracy of 75.6 on our test set. So we can actually see that we've slightly overfit the data, but that's okay. So here is one challenge to everyone over here participating right now. Try and see if you can you have this Colab notebook, right? Try and tweak the parameters to get the shallowest network possible that improves upon the score that I've achieved over here. I know that there are a lot of things that I haven't tried out, and if you have the time for it, you can basically try and then try to get a higher accuracy score on this set of data. After you're done, you can always save your model over here. I've added some starter code to just quickly save the model to mount a drive, and then to save the model as a HDFI file. So we'll be using this for the next part of our presentation. That basically wraps up my part, however, and I'll be handing it over to Stephen to basically talk about data scraping as well as wrapping up the workshop. So Stephen.
Okay, so I'll be sharing my screen back again. Give me a moment. Okay, so now that we've like discussed on the model itself, so you may be thinking, wow, I have my idea for Orbital. Now I want to like do that, do my model or whatever. So suppose you have that, and now you're thinking, so then how do I get my images? Where do I get them from? Then of course you think Google Images lah, or somewhere else. Now you'll need to, I guess, now create your own data set. I mean, first things first, if you can find a data set that works for your model online, you should start by using that as a baseline before you transition to using another model. So that would be like, if you can find one from the previously mentioned, like that set of stuff, like from Kaggle, from Google Image Data Set or whatever, you should try and use those first. Then if you cannot, then you should, then after that, you can transition to doing this like web scraping or data collection. Okay, so data collection. Yeah, so machine learning requires a lot of data. In very large companies, this is collected from their applications themselves, like for example, Shopee or whatever. They collect all your impressions on different items to kind of track and see what kind of preferences you might have for new items to recommend them to you in future. So, but then we're working from the ground up. We're working from our garage. So we have to work like Mr. Bezos here back in like, don't know, way back when, where Amazon was just this little garage project, and we gotta resort to one of these two different ways. So one would be web scraping, which we will be currently learning now, where with a more specialized use case that maybe not so many people are thinking about. I don't know, maybe we want like Pokemon data set, Pokemon images data set or something, Pokemon fan art or something, and you want to identify this like what kind of Pokemon or something like that. Or it's like you want to get like textual responses. So this is text data, you want to get textual responses to customer data. So this is where you might want to use like web scraping for like just normal text data, or Amazon Mechanical Turk, which is like expensive, where you're getting real people to give you data that you can use in these different things lah. Then the other one is to use the open science data source, data science community. Similar use cases have been applied before. So we're tapping on like previous generations of work. Often you'll find something similar, or like there are data sets that contain your current data. For example, CIFAR that Bharat previously showed actually contains, I think, 10 classes of different things as well. Okay, so now we are going to go into web scraping. So we need to learn a little bit, just the tiny bit about the web. So we need to know what's a HTML. HTML is essentially the basic building block of the web. Right now we are already on the website. We can, if you inspect this thing, it should be in some kind of header or whatever. So markup, meaning you get like text like this, title, body, header, div, etc. And then these things contain like attributes. If you've done like OOP, these are like attributes like class, style, and then like you can have multiple of them. So you can have multiple like values of attributes for some. Hello world. So hello is one, and then world itself is also another. I guess another value in this class. So then we also need to understand a little bit of what CSS is. So cascading style sheets kind of define the style of the internet. How is it rendered, displayed, animated? So this is just for your information a little bit. But basically, what you need to know about this is that it can be used to identify individual elements in the web page. Okay, and then the last thing, a word of caution on web scraping. So web scraping, right, when you use it, it's a similar kind of a signature to some web crawling technologies. And so web crawlers, right, there's this ethical constraints and guidelines that we need to understand, such as the robots.txt of each domain, and also prevents us from like flagging off DDoS or distributed denial of service protection, which can cause legal issues. So what is the most important takeaway? Do not send too many requests to a single web server all at once. And also do not like overload and send like 1,000 or like 1,000,000 requests all at once. So meaning we need, even though our computer is very fast, we can send a lot of requests. We want to maintain that it's like a little bit slower so that it seems a little bit more natural and human. Okay, so now we can kind of jump into the code. You can view this. I think Rama will be has sent the thing. Yeah. So data collection. Data collection is, once again, the collection of individual pieces of data to turn into the data set for use in analytics or training data for training a model. So this is part of the data pipeline. This is the initial ingestion of data. Yeah, once again, important note web scraping. I need to emphasize this. Prof. Zhao made me emphasize it actually also. So it's very important to note that we need to do this web scraping ethically. So what does that mean? It means that, for example, in this file, if you're disallowed from this, from a certain like part of the website, for example, so Mozilla.com, this is, you want to find the robots.txt of moz.com. So then we go to robots. You go to robots.txt, every site should have this, and you'll be able to see like what they allow and what they disallow. So for example, they will disallow you from going into anything in local/search. So if you try and web scrape into this portion, it's not allowed, and you might be subject to being flagged as DDoS, and like there are legal implications if you do so lah. So I need to emphasize that once more lah. So so do not overload the website and do not run these things on the incorrect domains. This article is pretty comprehensive as to how you can determine that lah. Okay, so let's like go a little bit into the code. So the process of web scraping, process of web scraping for like some static sites and like most sites is, so you derive the URL of the website, right? You examine the structure of the HTML. Then after that, you request the HTML web page via like a library. If it's not if you're not doing in Python, you'll use like something else lah. Then you navigate to decide web page HTML element. You clean the web page. Okay, I think this part is a little bit badly worded. Then we store the web page content into a data set / data storage. So let's begin with a static page like Indeed. Okay, so let's start the run up. So number one, we derive the URL. So we need to clean the URL by encoding special characters. Okay, so let's enter this into the web page so that we can kind of just see if it works. Okay, yeah, it kind of works. So when we just paste this into the website, we can kind of examine parts of the web page. So for example, we want to just scrape this part, right? We want to use our Chrome browser or Firefox browser, and we want to inspect the element. Ignore that. So when we inspect it, right, you will be able to see that you have like the part which you're looking at will glow lah. So you'll be able to see that you're actually looking at that part. So then if you remember before, the ID / classes. So this one has a class job title color purple. So these are some of the ways you can target this particular component in the web page. And so then you'll be able to understand from this that you can extract the text page from that. And I think we'll show you how to do that through this little notebook. Yeah. Okay, so we examine the structure, right? So we examine the structure. This is I believe is a GET request or something from Indeed. So in the Indeed URL, it'll send this information with these different arguments into the URL. If you want more of these like arguments, right, you can just add like some different parts here, and it will show you like more stuff lah, more arguments that you want to include. So this is just a subset of what you could be including. So this would translate to plain text, data science, $2000, 0000, then location New York, full-time. But then you see this has like a weird structure, right? With this %20, %24, and then 20 something, blah, 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 2C. So these are actually just encodings of that plain text, right? These plain text bits into URL encoding, which is using these some hexadecimal points. So if you want to transcribe in future, like like what these like what those what you call it, percentage signs mean in the URL. So then we kind of want to clean it. Okay, this is like my code from trying to figure that out. Right. Is it? Oh shit, it's hanging. Okay, give me some time. I think it's having a little bit of technical issues. Okay, I think I'll just run through the code while we are waiting for it to load, I guess. Okay, I'll just go through from this one while it's still working. Okay, so this is essentially some code to clean the web page. So we replace the actual value, the string value with the URL encoding format lah. There are other ways to do this, but this is the simple way that we want to use for simplicity. So then we create a URL, right? A URL to request the HTML from. So we want to request this web page from this loaded web page from our code here. So this is Indeed URL creator. You can examine it further to kind of see the logic. It's quite simplified. It's just adding a chains of like the data for each different argument component. Then we want to get the page. We actually use the request library to send a request to the server, which will then send us this page in HTML. Okay, is it running? Okay, I think I'll just maybe I'll try just using the actual one then. Okay, so let's just run through this. So we have the Indeed URL creator. Then also I examine from this web page that if we want to press the next one, we use we add like there's an offset at the end, at the very end, which has like a start equals 10. So this end start equals 10 determines like that we're on the first page or second page. So when we plus 10, we go to the second page. So that's how we can like, I guess, click through the different pages. Yeah. Okay. So as you can see, so then this goes to the second page. If we paste this into the web browser again, you can see we have the same thing, but now we are on the next page. So this kind of requires you to examine the HTML structure of the page in order to kind of determine how to click through and go through the different parts lah. Okay, next one is we request the page, right? So this is just a loop so that we guarantee that we find a page. The page.status code essentially is a HTML get request like success code. So only if it's 200, then we get like success that you return a web page. If it's any other code, it means that like either the web page is down or you are unable to access it for some reason. Then we pass it through BeautifulSoup. And so this is where you actually are able to pass out different parts lah. So when we find like maybe an ID, we can get the text inside lah. And just run it right now. So for example, this tells us the number of pages of content that we can click through. This is like 52. So there are 52 pages in total of this that match this search query. Next, by examining the web page to see the distinct CSS classes and HTML elements, we can determine and derive what we want to web scrape. So in this case, we're gonna just get like the table format of job title, salary, company, location, and the short description. So as you can kind of see, we are looking inside this kind of class, which is an unordered list. That's a HTML element that we can expand to kind of see that it contains all the different like card information. that we are looking for. So we isolate to find the so we can isolate to kind of find the text we want. So this is one example of it. We can just show you. So this is one example of it after we kind of find this particular class of job search results, find list item. If we open this, again, I'll demonstrate it here. Sorry, my computer's a little bit potato. Okay. So we can just kind of see visually and visually examine like what parts contain what we want. So as we can see here, we can actually we can Control F to find it. So inside this element, we can kind of Control F to find it if we know what we are looking for. So if we see inside, now we can examine that inside each of this is the content that we want, which is in a list that we are trying to access, essentially. And so when we look through, we can find the list item. And then this is the most useful part of the API. So by doing this, finding the next sibling, we are able to iterate through at that level rather than using a find or find all, where we aren't guaranteed that we're going to be iterating through this from individual list items to list items. Because perhaps there might be individual LI elements inside the code itself, or like inside of these cards themselves, which can cause you to get unexpected content. So then we can now kind of iterate through. This is essentially finding from the list item itself. When you identify one part of the content, right? This is also a BeautifulSoup component where you can also find more individual parts of the data. So for example, that when you get this ref.find class job search results list, you can think of it as you're getting this as this whole list as your object that you're passing through. So when you're finding anything inside, you'll only be searching within this UL item. Yeah. Okay, so then you can use the classes to kind of identify. You can also, this example of you using multiple IDs, class IDs at once. So company location. This would appear in the HTML text as company location space. This is how it will look like in the HTML text. And we can isolate doubly specific by using the two classes at the same time. So then now we can iterate through and we will get out our data. Okay, wait, okay, no, that's yeah, okay, this is the data, but it's in a little bit of a more messy way. Below, then you can now kind of use what we have done above to create a loop that can extract the sidecar jobs. You can show below you have this card at the side that if you click through each card, you'll enter a slightly different VJK that you can click through. Do remember to also add some delay. And that's a little exercise that you can just do on your own to see that you've kind of mastered the content in some sense. Yeah. Okay, the next one is Selenium. So Selenium is used in automation of a lot of Python, I've got a lot of web page tasks, and it's useful for kind of automating out some different things. Oh, what is this? Okay, just wait for this to kind of run. Now I'll have to restart the runtime. So these are just some like little steps to get the Selenium to run on Colab. Your experience might be different, and you should probably go to the Selenium website to kind of see how to install it for your system. Let's just wait for it to load here. Okay. Yikes, really slow. Okay, now that it's done, I think we can start this part. So this part is we're using Selenium to kind of work with dynamic web pages. So what are dynamic web pages? Dynamic web pages are something like Google Images. So for example, if we go through this, you can kind of see here that we have content that is loaded here because our web page is at this point. This is a kind of tactic that like Facebook and whatnot used to have like very long scrolling, long scrollable, essentially infinitely scrolling web pages, because content is like dynamically requested from the server. As you can see, there's a loading thing, then more images turn up. And so that's how it's different from Indeed, where the whole web page has already been loaded and we're able to use it like that. So essentially in this kind of scenario, we need to have something that helps us scroll down and scroll down and scroll down so that we can extract more images, in this case, image data from the web page, and so on and so on. Yeah, then like show more results and so on. So Selenium does that such that we can do this automatically. So now we're going to use the Selenium to kind of search for our docs. Yeah, so in this case, we have a search term query, and we will insert this into the search query kind of bar, which you can kind of find through here. So in this case, Google Plus images is how they showed it in our text. In our case, we're using just a doc, so it's a very simplified term. For these ones, the most important argument for that you need to add would be headless, so that you're not like if you run this locally, it will open a Chrome browser on your screen, and you'll be you can see it like actually scroll down and all that right next, like on your second monitor or whatever lah. But if you enable headless, then it won't display a screen for you. Okay, so let's just get to it. So notice we add a little bit of sleep so that like when we scroll down, we give some time for the image to load, as well as prevent ourselves from, how you say, flagging the DDoS kind of stuff. So in this case, we also need to examine each element to kind of examine it. In this case, we do have a deterministic like tag kind of class, so we can find the element by using that / image contains add class q something for LUWD. That thing doesn't mean anything, but it's standard throughout the web page. So that meaning that we can use it to extract data that we want. And then when we examine the image element itself, right, it will give us this download link, or this link where the image data actually comes from. So when we do this, we extract the links here, and then we request directly to this to get the image. So in this code here below, we are doing this set of tasks. We are iterating through each thumbnail to click on it. then we sleep on 1 second. Okay, actually, I should demonstrate it here. So we click on it, we wait for a second for the content to load. Then after that, after this loads and appears, we are able to then quote unquote inspect it. Of course, using a mouse and keyboard, we won't be able to do that. But essentially, they're copying the link address, and then they're appending it to our collection of image URLs. And this thing will run a while. Yeah, so the time.sleep is a little bit of a bottleneck, but if you just take it and run it in the background while it's working like this, you'll be able to work through it. And the HTTPS and .jpeg is to ensure that the HTMLs the URLs that we are extracting are indeed the kinds of files that we are looking for. In this code, we are only looking at JPEG files. So then we can also change the work directory and kind of add, make a new directory, this time in Colab. But your running version of Python might be different. That will essentially get us to have a new image, a file structure that we want. So then next we download and save each image into the file. Okay, this is going to run for a little while. And then essentially here we are using PIL, which is Python imaging library, to kind of save this file into RGB and JPEG with a certain quality. If you want more quality, you can increase it. So some of the images will be unable to be saved. If you run this through, could not be downloaded from certain URL, etc., etc. So essentially, this is the request.get. And then we can, since we are not guaranteed, if we want like 200, we should run it through some kind of while loop until it works till the end. I leave this part as an exercise. It shouldn't be too difficult. The code will be somewhat of a loop over the directory. Remember to also add adequate sleep time to prevent triggering any unforeseen circumstances. So then what's next? In the pipeline, right? The pipeline above, we have ingestion. So now we've ingested about 200 images. So now we need to pre-process it and make sure it's available for running our model. So Bara's like CIFAR 10 dataset is RGB data image dataset. So at this point, we have done a small bit of image processing already, but we might want to do a bit more. So when we open the file, we try and get the file names in image files. So we need to, this is quite important, that we need to resize it to 32 by 32 image 32 by 32 size, so that it's able to fit in our model. And then we can save that as the proper quality again. Let's see if we can get it to run. Okay, that part is finished, so we can continue with the next part. Then I'll just run this for like 1 or 2 images. Okay, as you can see, it's coming in. So if we refresh here, you'll be able to see we have data set, and then we have like a 0, 1, 2, blah, 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 blah. So let's just kind of see this in action for the first image. Is it? Oh, okay, it's a directory. Okay, wait, let me just debug this for a moment. Okay, I think they did run it. Okay, never mind. We'll just use we'll just copy this URL and we'll use it as we'll just copy this path and we'll use it as our test image. So we open this image and so we open this image and then we kind of see you can see it's quite big. It's like a pretty large data. It's quite a big file. It's a very cute dog, but it's pretty large. So we want to resize it down. And this is a short demonstration on that. Open that as well. Yeah, so then if we replace them with this, then we can reopen it. And so that it's been like resized down to something quite tiny. You have to zoom in order to actually see it. But that's like the actual 32 by 32. So it's pretty tiny. And yeah, that would be the second part of that data set. And here's one final example based on this Stack Overflow that does make use of both Selenium and BeautifulSoup, that loads the entire web page of one page of Shopee, and then requests the final static web page to kind of scrape it. So I think of note here would be the part where you scroll. So you scroll down to the bottom, meaning you load all the images of, I think the case that I had was like a bag. And then you get this as the HTML driver source, right? And then after that, you can pass it using BeautifulSoup. And this is a loop that kind of does that. Okay, that's the longer than expected kind of overview of web scraping. So now let's just talk about what we'll be doing next week. So next week, we'll be deploying models into production. We'll be showing you a short demo of what we'll be doing, like what I guess a RESTful API with a model would be like. And then we'll be showing you a bit on transfer learning, which is taking like deep learning models from open source and kind of fine tuning it using perhaps some of this data that we scraped and cleaned to make our own model with more specificity and using a very powerful model that is open source and used by others. Yeah, thanks so much. Do you have any questions? We have the Slido link once more, and I think I'll leave us on this slide while we answer questions. Oops. Okay, we have a question on data tagging. So I believe data tagging, right? If you have multiple objects in the image, that one would be done under something like image annotation. So there are a few different softwares that do that. Let me just Google them out for you. There are some different formats. I think one of the more common ones is like for label IMG, which is using like some kind of HTML parser that you can use. I'll link it right here so that you can, for your convenience. Yeah, so this one, right? I don't have time to demonstrate it, but like essentially you take parts of the image, right, and draw kind of bounding boxes over the different parts. I think you can follow the demo video or whatever they have in the software. There are also other kinds of software that do this. And then like this this format, right, is used by some different models. It's a little bit more complex than just like running it simply with in the training loop that we showed today. But like you can see some YouTube tutorials that will take you through that. If that answers your question. Let me find the slide though. Okay, so I'll just run through this one by one. What sequential model? If the person is still here, can you, I guess, answer again? Not sure what you mean by the sequential model, but I think the issue that was pointed out was that you are using like a slightly non-optimal neural network model, meaning like you're using like the fully connected layer for that part rather than using the part where maybe it'll be more used, like for the sequential. I think it was already answered. Oops. Yeah. Is it possible to use Selenium for Indeed? Yeah, it's definitely possible, but it's a bit overkill to use the Selenium for Indeed. It can definitely be used, and you can do the same thing by like requesting it, loading it, and then like sending the page source from the web driver to the BeautifulSoup HTML parser. Okay, the question for me: how did I get into this data science as a CS major? The data science kind of thing. Actually, I got into it because of a friend lah. So a friend, like, he's also from CS, but he did a bit of machine learning stuff. I think he's the previous president of Statistics Society, actually. And he was also a CS major, by the way. The AI focus area, it doesn't really cover what you are expecting at the 3 to 4K level. Okay, I think ML, the CS3244 will cover some of the machine learning to deep learning aspects at a broader level. But if you want to go in depth, you'll need to go at, I think, 5K, the neural networks 1/neural networks 2, or like some of the more other like 4 to 5K mods for more data sciencey stuff. Yeah. Any more questions? I think we'll stay around for another like 1 or 2 minutes.
To answer the question in the chat, good NN model for NLP. All right, so until a couple of years ago, the state of the art was using long short-term memory, or LSTM, or gated recurrent units, both of which are variations on recurrent neural networks. So RNN, right? But then right now, transformer models are in vogue. Transformers, so basically stuff like BERT are currently the cutting edge.
Okay, I think one other point that you want to think about is also like whether like the state of the art on it, right, is the most optimal for your use case. Because ultimately, when we're thinking about projects and all that, right, we also want to think about scalability. So if your project is like an online thing where you're serving some kind of service from server to a user, right? If it's not downloaded on their own computer or whatever, anyway, it is downloaded on their own computer, you want to think about is their computer able to handle the running time? For example, you just saw an example of me. I don't know why my MacBook is struggling with the Google Colab, but you want to think about scalability. So that might also play a part in whether you want to use the very bestest state-of-the-art model rather than like something maybe a little bit less like high compute power, but like high predictive power, but also high computational costs. So you should also select based on that lah, and what is your tolerance for accuracy, essentially. Okay, Any last questions? If not, I think we can close off the session for today. And I think I'll stop recording.